Welcome to Physics 3. This is your first video in Chapter 19, dealing with thermodynamics. We're going to start with the 0th law of thermodynamics. The first two laws of thermodynamics have been pretty much established. Conservation of energy, the law of entropy, the idea of disorder increasing as function of time. So once those had already been established, it was determined that they really needed a law before that, one that established the definition of temperature. So there's the 0th law of thermodynamics. It goes like this. If body A is in thermal equilibrium with body C, and if body B is in thermal equilibrium with body C, so in this case A and B are themselves in thermal equilibrium with body C, which is our thermometer, then it's true that A and B will be in thermal equilibrium with each other if they happen to be placed in thermal contact, which means that if they were placed in thermal contact, there would be no heat exchange from one to the other. They would have thermal equilibrium. This allows us to establish a temperature based on body C. So they are said to be at the same temperature, and thermal equilibrium will result when two objects cease to have heat exchange between them, and we can use then body C as our measurement of that. Celsius and Kelvin scale, Celsius or centigrade scale, and the Kelvin scale. The Celsius temperature defines 0 degrees as the ice point of water, the freezing point of water, where it goes through a phase change, liquid to solid, and vice versa. And 100 degrees Celsius as the steam point of water, where it does the other phase change from liquid to gas, and vice versa. The Kelvin temperature relates to the Celsius temperature. Temperature in Kelvin is the Celsius temperature plus 273.15. This allows us to establish the Kelvin temperature as starting at absolute 0. So 0 on the Kelvin scale is actually 0 absolute. We use the Fahrenheit scale in our everyday lives. Why? Well, 0 to 100 on a Fahrenheit scale is livable for human beings. 0 is freezing. 100 is you can be outside and still survive at 100 degrees. You can play tennis at 100 degrees Fahrenheit and 0 degrees Fahrenheit. I've done it. So it's possible to live under these conditions with proper clothing. On the Celsius scale, 0 on the Celsius scale is freezing, but 100 degrees on the Celsius scale is boiling water, and you can't live under those conditions. 0 on the Kelvin scale is absolute 0. Everything stops. It's about as cold as you can get. And 100 degrees on the Kelvin scale is still liquid nitrogen temperature, is still pretty cold. So Fahrenheit is easier for us to live with, but Kelvin for science is the best way to go, because we start at 0. There are no negative temperatures. Everything is positive from there. Here's a logarithmic Kelvin scale starting from 0. Lowest temperature achieved is about 1/1,000,000th of a degree Kelvin. So you go up from there. Liquid helium is 4.2 degrees Kelvin. If you take liquid helium and you were to evacuate the atmosphere above the liquid helium, you would force molecules to want to leave the liquid and take energy to move into that vacuum. Hence, you can cool the liquid helium down further as it's losing energy to the gas. And you can get it down to 1.6 Kelvin. I've done it that time before. Liquid hydrogen. Hydrogen solidifies at 14 degrees Kelvin and hence becomes liquid as you warm up from 14 degrees Kelvin. Liquid nitrogen is established at 77 degrees Kelvin. Still pretty cold, but relatively warm compared to absolute 0. High temperature superconductors transition just above 77 degrees Kelvin, so You can use liquid nitrogen, very easy to use, and use your high temperature superconductors in that range. Water freezes at 273 degrees Kelvin, hence for the correction between centigrade and Kelvin scale. Copper melts somewhere around 1,000 degrees Kelvin. The surface of the sun is 6,000 degrees Kelvin, and also happens to be about the temperature of the middle of the Earth. The interior of the sun, the very interior of the sun, where fusion takes place, is on the order of 10 million degrees Kelvin. You need those kind of temperatures to bring the nuclei together so that fusion can take place. Hydrogen bomb, somewhere on the order of 100 million degrees Kelvin. So it can recreate the conditions better, create the conditions of the interior of the sun at the center of a hydrogen bomb. Hopefully we never have to experience that. But it tells you the challenges of trying to use fusion as a method of energy production. Fahrenheit scale defines 32 degrees Fahrenheit as the ice point of water, 212 degrees Fahrenheit as the steam point of water. A difference of 180 degrees. Hence, every Celsius degree is 9/5 that of a Fahrenheit degree. Or we could write it like this. The temperature in Fahrenheit is 9/5 times the temperature in Celsius plus 32. This is our basic conversion. And we can go the other way around. If we subtract 32 from both sides, divide by or multiply by 5/9, then you can convert from Fahrenheit to Celsius. The change in temperature on the Kelvin scale is the same as a change in temperature on the Celsius scale. So those change in temperatures are the same. Can be very useful if you're dealing with changes in temperature, which many problems will just deal with a change in temperature rather than the absolute temperature itself. The change in temperature on the Fahrenheit scale is 9/5 that of a change in temperature on the Celsius scale. Again, very useful for the problems yet to come, because many of the problems will be dealing with changes in temperature and not necessarily specific temperatures. So these are very, very useful formulas. Here's a proof of this change relationship. If I say my temperature in Fahrenheit initially is equal to 9/5 times my temperature in Celsius initially, plus 32, and do the same thing for my final temperature in Fahrenheit has the same kind of relationship to the final temperature in Celsius, then my change in temperature in Fahrenheit will be the change of these two temperatures. As I make my conversion, I have 9/5 temperature in Celsius final plus 32 minus 9/5 temperature in Celsius initial plus 32. 32 minus 32 cancel out. And I have 9/5 final temperature Celsius minus initial temperature Celsius, which would be 9/5 times my change in temperature Celsius. So again, rather than having to use these individual conversion formulas, the change in temperature is easily done in conversion between these temperature systems. Thermal expansion of solids and liquids. For solids, the change of length of a solid, a one-dimensional solid, is proportional to its original length and proportional to the change in temperature. And that proportionality constant is this constant alpha. Looks like this. Here's my original length, L naught, and then after a change in temperature, it is increased in length. So this change in length is proportional to the original length and that change in temperature. Alpha is the coefficient of linear expansion. It would be intrinsic value of whatever material you're using, whether it be copper, steel, aluminum, you name it, they're going to have different linear expansion coefficients. So our new length is going to be our original length, L naught, plus this change in length. And that'll be L naught plus alpha L naught delta T, which we could write as our original length L naught 1 plus alpha delta T. Alpha in general is going to be a relatively small number. Change in T is just the change in temperature, most likely either in Kelvin or Celsius. It won't matter if you're on those scales because you're dealing with a change in temperature. A two-dimensional thermal expansion can be seen as a magnification both of the object and whatever hole or impression you have. For instance, this washer, if we were to heat this up, it would expand, and that all the dimensions would expand, and so would the hole. So even though the hole is not made of any material itself, that's going to expand just like the material that is surrounding it, in a sense. You can think that if the hole were filled with that material, the material should expand accordingly, and hence all the other material will expand accordingly as well. So if that middle material is gone, the rest of the material will still expand in like fashion. Here's an application. You can loosen a tight metal lid on a glass jar by running hot water over it, and hence the metal will expand more than the glass, and that will make it less tight, and you should be able to unscrew it more easily. Another point here, we're talking about a two-dimensional expansion in this particular case of the hole. Any one dimension, though, on this object will expand according to linear expansion coefficient. So if I were thinking about the diameter of this hole, I could find out how much the diameter expanded by using the linear expansion as opposed to what we're going to calculate for the area expansion. Here's another application, a thermostat bimetallic strip. Let's say one strip is made out of brass with a linear coefficient of 19 times 10 to the minus 6 per degree Celsius, and the other strip is made out of steel with a linear coefficient of 11 times 10 to the minus 6 per degree Celsius, almost a 2-to-1 ratio in the way that they expand. So if the temperature were to go up, with the brass expanding more than the steel, we would have this kind of situation where the brass is expanding more this way and the steel is expanding less. So there's going to be a torque on this last metal piece there, and because of that torque it's going to rotate, and because it rotates, it'll rotate away from making an electrical contact here, and hence it will stop the electrical circuit. So because of the change in temperature, this will stop whatever electrical circuit you have and shut things down. And that's what a thermostat should do. It should shut things down when you've reached the proper temperature. So it works pretty neat, just using the linear expansion properties of these materials. So let's calculate the expansion of an area. Let's say we had an area, initial area of this square is L naught squared, and we heat it up, and there should be a linear expansion in any particular one dimension that we're looking at. So let's say expanded, and now our new area is L squared, where each dimension has expanded to L. If we make our substitution for each linear dimension L, our new area is L squared, which is L naught 1 plus alpha delta T squared. If I expand this, I'll have L naught squared times 1 plus 2 alpha delta T plus alpha squared delta T squared. Now we saw from the previous example of the bimetallic strip that alpha is on the order of 10 to the minus 6. So I'm going to have 1 plus a number that's pretty small here, 2 alpha delta T. That's really going to be pretty small. And then I go to the next term, alpha squared delta T squared. Alpha squared will be 10 to the minus 6 squared, and delta T will be some number squared, but nothing in comparison to 10 to the minus 6. So this second term is going to be incredibly small. so small that it's basically insignificant compared to the other two terms. So we're going to just say that that is basically 0. So we have that the area is equal to our original area, L naught squared, times 1 plus 2 alpha delta t. So for area, our expansion coefficient, which we call gamma, is actually equal to 2 alpha, where alpha was the linear coefficient. Very good. So for a linear expansion, we have our length is equal to L naught, 1 plus alpha delta t. For an area expansion, we have our area is equal to A naught, 1 plus gamma delta t, where gamma is equal to 2 alpha. So if I know alpha for this material, I can get my area coefficient from that. And by golly, for volume expansion, when we're looking at 3 dimensions, volume will equal our original volume, 1 plus beta delta t, where beta is equal to 3 alpha. And we could prove this very easily using the same kind of mathematics we did on the previous screen, where we had expansion for 3 terms, and the small terms will all basically be 0, and we'll end up with beta equal to 3 alpha. So that's kind of a nice thing to remember. If we know alpha, we know the area expansion as well as the linear, and then we know the volume expansion as well. So let's try an example. Does this hole get any bigger or smaller? A hole of cross-section area, 100 square centimeters, is cut into a piece of steel at 20 degrees Celsius. What is the area of the hole if the steel is heated from 20 degrees Celsius to 100 degrees Celsius? So we're going to have a temperature change of 80 degrees. So here's the hole. Original area 100 square centimeters. And the hole will expand exactly like the surrounding material, because if it were filled with that same surrounding material, that would expand as well. So, and everything around it will expand accordingly. So it's almost as if it were filled by the same material, but it will expand like the same as the surrounding material. So we're going to heat it up. It'll expand. Our new area will equal our original area, 1 plus 2 alpha delta t. Alpha for steel is 11 times 10 to the minus 6. So our new area is 100 times 1 plus 2 times 11 times 10 to the minus 6. Change in temperature is 80 degrees Celsius. And we have a new area that is 100.18 square centimeters. That is the new area of the hole in the middle of this washer. All right, so that concludes the first short lecture in this chapter 19. The next short lecture is going to be on the ideal gas law. So look for that